According to Richard Feynman, the particle and the two-slit experiment contains the main mystery of quantum mechanics. He is quoted saying, "We choose to examine a phenomenon which is impossible, absolutely impossible, to explain in any classical way, and which has in it the heart of quantum mechanics. In reality, it contains the only mystery. We cannot make the mystery go away by explaining how it works. We will just tell you how it works. In telling you how it works, we will have told you about the basic peculiarities of all quantum mechanics." Indeed, it is mysterious how a point-like particle such as an electron would know when one or two slits are open. When one slit is open, the electron would form part of a simple pattern, while when both slits are open, the electron would form part of a more complex pattern. Consider a large wall with two pinholes sitting in a vacuum, as seen. The vacuum contains all possible quantum waves. There are quantum waves of many different wavelengths interacting with the wall. Depending on the wavelength, some will make narrower cones and some wider cones as the waves go through the pinholes. Some waves propagate to the right and some to the left. Other waves propagate at different angles with respect to the wall. If we would attempt to draw all the waves at once, we would not see anything, since there are so many of them. All of this happens even if there is not a single particle present. One of the waves is a quantum wave, moving to the right. Left of the wall, the wave is a plane wave. Right of the wall, the wave has two cones emanating out of the pinholes. The cones will intersect and form regions of constructive and destructive interference. We note that if one of the pinholes was closed, then we would only observe a single cone and no interference. Now, we assume that a particle moving to the right comes from far away. The particle momentum equals h over lambda, corresponds to the wavelength of the quantum wave. We assume that the incoming particle is only connected with the quantum wave depicted. Then, the other quantum waves would be invisible to this particle. If the particle goes through one of the two pinholes, it will eventually hit a screen located somewhere right off the wall. When the particle passes near a pinhole, it could be deflected in any direction. For the particle to be deflected, momentum is required. Virtual particles that propagate between the trillions of molecules that make up the wall and the particle transmit momentum. This exchange of virtual particles is guided by the quantum wave connected to the particle. Since the quantum wave right of the wall has regions of constructive and destructive interference, it is likely that the particle would be deflected along a path of constructive interference.
The exchange of virtual particles is the mechanism that the quantum wave uses to stir particles. It is possible that the particle was not deflected when it passed near a pinhole. The reason is that the launching of a virtual particle is a probabilistic occurrence. Let us suppose that the particle, after crossing a pinhole, moves along a dark fringe, but the particle should not be found in a dark fringe. Eventually, the particle will get close to the detector screen. However, as the particle is ready to be detected at a dark fringe, it has one more chance to move to a bright fringe. The molecules that make us the screen could transmit momentum to the particle through virtual particles to move the particle from the dark to the bright fringe. In the end, it is quite likely that the particle would hit the screen at a bright fringe, where constructive interference occurs. The hit would be recorded as a point on the screen. When the particle hits the screen, it leaves a mark, which constitutes a measurement. At measurement, the particle vacates the quantum wave and could occupy a quantum wave packet, or it could get absorbed. If the particle was an electron, it could end up taking an empty quantum wave packet produced by molecules that form the screen. We note that the quantum wave would not collapse after being vacated by the particle. Except for the information about its state of occupancy, the quantum wave would remain unchanged. The experiment could be run at a rate low enough so that at any given time there is only one particle in the entire setup. The many identically prepared particles would be guided by the same quantum wave. The collection of many particles would eventually form on the screen an interference pattern with bright and dark fringes. If the particle source was near the wall, then a quantum wave connected with a particle would be a wave packet. A wave packet can be considered as the sum of many plane waves. Thus, the dynamics of the wave packets would be similar to the plane wave described before. The main difference is that the number of possible outcomes of a particle after going through the pinholes would be greater than that of a single plane wave. The dynamics of virtual particles that deflect particles would be dictated by the wave packet rather than the plane wave. If we decide to investigate through which pinhole the particle goes through, we could block one of the pinholes. When a pinhole is blocked, we have changed boundary conditions, which result in different wave interference. Now, right off the wall, there would be a single cone that by itself produces no interference. Virtual particles would be fired so that the particle would follow the single cone pattern. However, we may decide to obtain information about which pinhole the particle crosses using a mechanism that partially blocks the pinholes. Imagine that the particles that come from far away were electrons, and a source of photons was placed behind the pinholes. The setup would be such that whenever a scattered photon would be detected, we would know which pinhole the electron crossed. As it is well known, this does not work either. The uncertainty principle keeps us from getting information about which pinhole each electron crosses through, while simultaneously maintaining an interference pattern.
We first analyzed the delayed choice experiment originally proposed by Wheeler. A single photon enters a Mach-Zehnder setup, as in Figure 2, and reaches a 50-50 beam splitter. Right before the photon reaches the intersection where the beams cross, we have the choice of placing or not placing a second beam splitter. In setup 1, we do not place the second beam splitter and the photon ends up at one of the detectors, as in Figure 2. Applying energy momentum conservation, we extrapolate the path of the photon from the detector all of the way to the initial entrance and obtain full particle information as given by the path. In setup 2, a second beam splitter is inserted as in Figure 3. Setup 2 is arranged so that the destructive interference is produced along the path that reaches one detector and constructive interference is produced along the other path. In this case, the photon will end up at the detector with the path that shows constructive interference. In the delayed choice experiment, we will wait until the last picosecond before the photon reaches the intersection to make the choice of whether to use setup 1 or setup 2. We note that the delayed choice experiment has been experimentally realized. According to Wheeler, the consequences of our choice are paradoxical. If we choose setup 1, the photon has taken a single path. If we choose setup 2, the photon has taken both paths. What is striking here is that the choice of the observer affects the past history of the photon. There, in what is commonly called the delayed choice experiment, we make the decision whether to put the final half-silver mirror in place or to take it out at the very last picosecond, after the photon has already accomplished its travel. In this sense, we have strange inversion of the normal order of time. We now, by moving the mirror in or out, have an unavoidable effect on what we have a right to say about the already past history of that photon. Here is how we understand the delayed choice experiment within our model. The particle and the accompanying wave packet enter the Mach-Zehnder setup as in Figure 2. The 50-50 beam splitter splits the wave packet equally, while the point-like particle takes one of the two equally likely paths. Right before the photon reaches the intersection, we have the choice of placing or not placing a second beam splitter. If we do not place the second beam splitter, the particle would continue and activate a detector as in Figure 2. Applying energy momentum conservation, we would extrapolate the path of the particle from the excited detector all the way to the initial entrance and would obtain full path information. We note that in our model, the empty wave packet that reaches detector 2 could not activate it, as it has no significant energy or momentum. Had we placed the second beam splitter as in Figure 3, we would never see the particle reaching one of the detectors due to the destructive interference. We note that in this case, within the beam splitters, the actual path of the point-like particle would be unique. Therefore, according to our model, there is no paradox. Moving in or out of the second beam splitter has no effect on the past history of that photon. In setup 1 and setup 2, the wave packets always occupy the available paths within the beam splitters, while the particle is always in a single path.